What's going on, everybody? High Peak Education, new problem coming at you, namely having to do with gravity forces. So let's go ahead and perform this calculation. It says that the sun has a mass of 1.99 times 10 to the 30th kilograms. Earth is at an average distance of 1.50 times 10 to the 8th kilometers from the sun. And we know the gravitational constant is 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. What is the force of sun's gravity at Earth's distance? Okay, so let's go ahead and write down our knowns. So we know that the mass of the sun is 1.99 times 10 to the 30th kilograms. We also know the average distance that the Earth is from the sun. And let's assume this is the average distance from the center of the sun to the center of the Earth. So that's going to be a radius. And that's going to be, let's put that in meters. So that's 1.50 times 10 to the 11th meters. Many things in astronomy are expressed in kilometers, but here we go. Now, we also are going to need the mass of the Earth. So the mass of the Earth is about 5.98 times 10 to the 24th kilograms. The fact that I know that makes me a big nerd. What is the force of sun's gravity? So we want to figure out the gravity force coming from the sun. And we know what the gravitational constant is. So there we go. All right, I think we can just plug in because we know what the universal gravity force is. So big G, and that's going to be mass of the Earth times the mass of the sun divided by the radius squared between them. That is to say, G mass 1, mass 2 over distance between the centers of mass squared. So let's put all the numbers in. This is 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. That multiplied by mass of the Earth, 5.98 times 10 to the 24th kilograms, times the mass of the sun, 1.99 times 10 to the 30th kilograms, and divide that all by the radius. And that's 1.50 times 10 to the 11th meters, and we have to square that. Okay, so let's go ahead and put this in our... Okay, so let's make sure our calculator, when we go to mode, let's make sure we're in scientific notation mode. Let's second quit. And then now let's do alpha F1 and get a fraction stack. And let's make sure we put these values in properly. So we're going to go 6.67 times 10 to the minus 11th power times 5.98 times 10 to the 24th, that's kilograms, times 1.99 times 10 to the 30th, and we'll go down and we'll divide that by 1.50 times 10 to the 11th, and we'll have to make sure we square that in the denominator because the inverse squared law. Okay, so we have this number. Let's write this down. It's about 3.53 times 10 to the 22nd. So approximately 3.53 times 10 to the 22nd, and that's going to be newtons because this is a force. So this should be the approximate gravitational force that the sun exerts on the Earth, and the same force that the Earth exerts back on the sun. But the sun is so much more massive. In fact, you can see it's about 1,000,000 times or so more massive than the Earth. So we're not going to affect the motion of the sun nearly as much as Earth is tied in orbiting around the sun. Okay, so this is how we solve these gravitational force problems. Thank you very much for your attention. Please smash that like button if you enjoyed this content. Please subscribe to the channel to grow the channel. Please share this amongst your social networks. Thank you for watching High Peak Education. I will see you in the next video.